Hello everyone. So welcome to the second lecture of third day. We have Felix Schulze. So he will over to you.
Okay, thank you so much. Now let's continue with the final lecture of the series. Let's maybe recall the setup a bit. Okay, so what was the setup? Now we consider first our boundary. This is gamma n minus 1 in n plus 1, smooth, closed, embedded, and oriented. So this is sort of, think of it like this. So this is our gamma. We call it gamma 0. Okay. Now we take an area minimizer spanned by gamma 0. Might have singularities here. Yeah? Okay. Now this attains its boundary data smoothly, so we can think of the normal bundle here sort of off. So here's the minimizer, sigma 0 here. So this is the normal bundle to sigma 0 restricted to gamma 0 on the boundary. This is one-dimensional. Now we can think of here doing a monotone or just equidistant perturbation of the boundary data in direction of this normal bundle, for example. This would be 1. This would be for a bigger parameter. So let's say this is gamma s, and this is gamma s prime, and we have the minimizers here. This would be sigma s, and this would be sigma s prime. Yeah? So we have, what is the setup? We have sigma s is minimizing such that boundary of sigma s is gamma s. As I asked you to just believe this, that we can arrange that, or this is always true, that sigma s and sigma s prime are pairwise disjoint. It's a strong maximum principle. And then we looked at the following function, the following parameter function, this timestamp function, was tau of x. We define it as being s for all x in sigma s. And now we look at this combined singular set. So we put all these singular sets together. So this combined singular set S is just the union over S over the singular sets of sigma S. Now we restrict this timestamp function to this combined singular set. It's now a map into, let's say, 0 delta. Okay. And what was the aim? So how we want to prove the whole thing is we want to prove that this image in this interval 0 delta has Hausdorff dimension less than 1. So this means we find arbitrarily close to 0, or everywhere in every interval there are points which we don't hit. These pre-images correspond to leaves which are nice and smooth. What we did in the last lecture, we proved actually more. I said this goes back sort of on these ideas of Hart and Simon. If n plus 1 is equal to 8, then we argued that this singular set S, this combined singular set, let's say not this here, sorry, right, this tau of S is discrete. So even better in that case. Okay, now let's come to higher dimensions. Are there questions so far, maybe before I continue with the setup?
No.
Okay. Okay, good. Let's go to higher dimensions. Okay, let's recall a few things we need there. We discussed them already in the last two lectures. Assume we have a point x in this minimizer, in the area minimizer sigma s. Okay, what we of course know is that if we look at the area ratios, the map R to theta of sigma s x r, this is increasing in R. Remember, this was important here. And we had the following statement. If we look at theta of, let's say, sigma s, point x, r, minus theta of sigma s x, let's take r over 2. Remember, if this is equal to 0, we know we are on a piece of a cone, but we argued that by compactness, that if this is small, if this is less than epsilon, then we get, okay, let's do a bit more precise statement. This time we take sigma s, we center it at x, we now rescale by this factor r. Now you see, so this means I rescale this factor r to 1. So this means this is close to a cone C. On which interval? On B1 without B1 half. Okay. Now you see, now you have to look at this. So this means if, so what does this mean? This means if we know that, but just as a reminder, we know that theta of sigma s x r converges to the density as r goes to 0, okay? So this means if this difference here between these two is less than epsilon, then between any two scales r and r over 2, we are close to a cone. See? Okay, so this means even if we start like at scale 1, there are only finitely many scales where we're not close to a cone. So this means if we consider, so this is called quantitative stratification or differentiation. Yeah. So consider, if you've heard this, consider now we do dyadic scales. Rj is like 2 to the minus j. Okay. So what do we get? Let's say j greater or equal than 0. Now, for all but finitely many, you see, we can only finitely many times drop an amount of epsilon, otherwise we are smaller. So for all but finitely many j, we have that rj to the minus 1 sigma s minus x is close to a cone. The cone might depend on j. Let's call it Cj on B1 without B1 half. So this means is as we zoom in, we see all these models of minimal cones which sort of start modeling the singularity. Okay, now let's remember here what was in this Hart and Simon argument. Let's go back to last time. This was the important theorem of Hart-Simon. This was this kind of in R8. So we assumed that the cone is minimizing and has a singularity only at the origin. Then we could prove this, or there's this Liouville theorem saying that if you have an area minimizing surface on one side of this cone, then it's one of these unique elements of the smooth foliation, or the cone itself. That was the important ingredient. But the important ingredient here to prove this is this assumption that the singularity of the cone is only the origin. This does not work without it. It's known in a few cases, but that these very few cases you can prove also uniqueness. But even if it has seen later, this argument here, this argument also we had here, this blow-up argument dependent on the cone here owning being singular at the origin. If this cone would have like a single line, a spine, this argument would break down. Because I see in this end, the singular point could run into the spine. So this argument of Hart and Simon really only works in R8. Okay. Now, what we do now here is we found an very easy kind of cheap replacement of Hart and Simon. It's a weaker statement, but we can use it more generally. So this is this proposition. And it's a kind of, one can see it as an infinitesimal Hart-Simon result. So this is in our first work in this, yeah. So here the statement as follows: if you have a cone in Rn plus 1, which is non-flat, minimizing cone. So the important thing is this cone here, there's no assumption on how the singular set of this cone looks like. This can be completely general. Yeah? So you can hear this area minimizing cone. Then assume you have here a sigma in either in U plus minus, you can take closure. Yeah? So on one side of this cone, which is area minimizing. And let's assume that it's conical around some point P in the singular set of sigma. Okay. Now P does not need to be 0. Good. So, out of time reasons, I'll not give the proof, but the proof is 1 page or half a page. So it's a very quick argument. This, in comparison to this result of Hart and Simon, this is much more difficult. Hart and Simon is a much longer, difficult argument. You have to understand the asymptotics and everything. This is a very quick argument using Jacobi fields. Okay, so then, okay, what is the statement? Sorry, what is the statement here? The statement is then sigma is equal to C. Yeah, so this is also kind of a Liouville type theorem, but for cones, yeah, and P is in the spine of C. So this means if I have an area minimizing cone, which is non-flat, so not the trivial flat cone, yeah? Flat means it's not trivial Rn. If I have one area minimizing cone sitting on one side of the other, you see this is much stronger. It's a much stronger assumption. Then both cones have to coincide, and any singular point of the second cone has to sit in the spine of the first cone. You see? So this is much easier to prove. And the idea is this works without an assumption, the assumption that the singular set is just the origin of the original cone, but it's enough to get the argument to work. Yeah. Okay, so what are the consequences? Let's maybe first, are there any questions regarding this statement? So we read, it's like Hart and Simon. So this Liouville type theorem where we said, okay, we have an area minimizing surface on one side. So you remember here it was an area minimizing surface on one side of a cone. The assumption was that this cone also has the singularity only at the origin. Then we know we're equal, then we leave off the foliation or the cone itself. Here we say, okay, we assume that the sigma is another cone. It sits on one side of this original cone. Then these two cones have to agree, and this second conical point, this is more or less a trivial statement, then sits in the spine of the cone. Okay, and again, the benefit is this is much easier to prove, but what are the consequences of this? Okay, now, see, let's recall this here. So you see this statement here before, we know for many, many scales here, we know that these surfaces are close to cones, yeah, up to finitely many scales. So this means if we look at two leaves which sit next to each other, yeah, so then we can assume we can just throw away these scales where we know we're not close to a cone. That can assume that nearby singularities at the right scales of disjoint leaves to assume that they're close to each other at the scale, we're looking at sigma s prime at scales rj, yeah, are modeled on cones CS prime, yeah, that we had seen that if we throw away finitely many scales, we can assume this, but these two cones have to sit on each side of each other. Okay, so what does this statement say? This statement here says, if we sort of use compactness, this statement says they're actually modeled on the same cone. This means that actually sigma s prime and sigma s are modeled on same cone C. Okay, now this is the first thing. The second thing, so this is part of this first statement here of this one. This is sort of the consequence of this here. Now, if you look that the singular point has to sit in the spine, this means all singular points here and all singular points here have to be modeled on the spine of this cone. Yeah? So the second thing is that the singularities of sigma s union, let's say, singular set sigma s prime, are close to the spine of C. Okay? Both of them are close. And we know this for any two leaves in this foliation. If you take, for example, fix S and let S prime vary a bit. So what does this give? This gives that this combined singular set, let's say near any point X we look at scale Rj, is coarsely the dimension of this spine C. If you do the right covering argument, the dimension of the singular set, it's modeled on this spine, so it's kind of coarsely has this dimension of the spine. This combined singular set. Because we know here that all the singular points, they kind of are in the limit close to the spine. So if you do a compactness argument, they're cluster close to a spine. We can always find a spine direction, where we kind of, this models the combined singular set at this point. Now, okay, here's a third point. Any questions regarding these first 2 points? I know this is a bit more hand-wavy now. I have to be a bit quicker, but this is sort of the idea. Now, let's look at the following thing. Let's look at, now we have this one, let's say we have this, so this, let's say this is sigma s. Here's the singular set, and we have sigma s prime, and they're both modeled on this cone C. They roughly look like this cone C. Okay, that would be kind of the picture. Now what you can look at, you look here on this cone at the regular set on this cone. We know smooth point is singular points converge to singular points, so that's where this guy here is nice and smooth. We get also nice and smooth convergence here of this one towards the other one. This means we can look at here at the normal height function u. We write sigma s prime as a normal graph over sigma s. Okay, so consider normal normal height function u of sigma s prime over sigma s. Okay, now what do we know now here? Let's say if we now do a limit of this guys, then this height function will go to 0. They converge to the same cone. Now we know we have the minimal surface equation. And what is the linearization of the minimal surface equation? Is here the Jacobi equation. So this means if we now if we take a limit, so the normalized height up to higher order terms, normalized height u of, okay, let's call this maybe u bar, so we have to kind of renormalize it. So it is like L2 norm 1, or usually we use rescale 1 point to height 1 and then use the Harnack inequality to push this around, to renormalize everywhere, of sigma s prime over sigma s. So what does this do? This produces a positive, this u has a sign, it's there on one side of it, positive Jacobi field u bar on this cone C. What this means, a Jacobi field, this is the linearization of the minimal surface equation. This would be Laplace u bar plus a squared u bar is equal to 0, and we can assume that u bar is positive. So this means if I want to understand how, so if I take the graphical height of this surface over the other one, I take a limit, I renormalize this then, or think of it not a limit, but I think, okay, this is, you do a Taylor expansion, here you see the first the linear order, then higher order terms. This here will be a graph over C as well. So in the end, we get the first order linear term will be a Jacobi field, a positive Jacobi field on this cone. So if you want to understand to first order how these two leaves behave towards each other, we can study positive Jacobi fields on these cones. So to first order, so we linearize the problem. So to first order, to understand how these two leaves behave towards each other, we can look at how Jacobi fields on these cones behave. You can think of this as kind of linearizing the problem. Both these surfaces are modeled on this cone, are close to a cone. Now we want to understand how they behave relative to each other. To understand this in the first order linearization, this gives us to get the Jacobi field on this cone here. So if we understand Jacobi fields on these cones, we understand to first order how two leaves behave towards each other. What the idea is, what we want to prove is that there's a decay rate, how these leaves decay, that these leaves decay towards each other as we go out. Okay, so what we need to do now is Jacobi field analysis. Okay, now this goes back to work of Leon Simon when the link is smooth, and work of Jonathan Zhu if the link is non-smooth. There's an argument as follows. So what is the statement? For each minimizing cone, so no restriction on the singular set, there exists an alpha of C in R, let's say in R plus actually, so R plus with 0 included, such that all positive Jacobi fields, now you see in minimizing cone, this only gets interesting from n plus 1 equal to 8 on, otherwise it's flat. Positive Jacobi fields on C, decay like, so we get a decay rate, that U is less or equal to some R to the minus alpha of C, depending on this cone. We might have to adjust little O of 1, so if you go out to infinity, you get this alpha, but maybe to a small error. O of 1 is here, and the little O of 1 is in terms of the radius. So we get a decay. So what do we get? So alpha of a hyperplane, of course, if you think what is the hyperplane, you can just translate the hyperplane up and down, so this means the Jacobi field there would be just a constant function, so we can't expect any decay rate. So for a hyperplane, this is 0. For a hyperplane, we do not have any decay. Yeah, but now the interesting thing is, for all non-flat minimizing cones, in Rn plus 1, one can prove that alpha of C is greater or equal than the alpha of the quadratic cones. Remember what let's call this alpha of n. Remember the quadratic cones were the CPQ cones. One can prove here that this is always bounded from below. We have at least a decay rate as fast as the quadratic cones. And you can actually compute these numbers for the quadratic cones. There you can write them down explicitly. Here I can show, okay, alpha 7. So this means if you only have a singularity at the origin, this one is 2. A pretty fast decay rate. And then it starts going down, alpha 8. But we can always prove that this is bigger than 1. And you can compute these numbers. Okay, now why does this help us? Okay, so what does this give us? This gives us here that if we have in this picture here, in this case, this gives us sort of a decay rate, how these two leaves on small scales where they're modeled on cones, how the two first order have to decay towards each other. So this means if you look at this foliation close to a singular point, then the leaves closest to the singular point start pulling apart. They pull apart. As we go out, they pull together. You can think it also as you go into the combined singular set, they start pulling apart. Okay, now what does it give us? Let's do a picture here. So where's the basic example here? Again, an example we have seen many times now. And we look again at these minimizing leaves. On either side of the Simon's cone. Okay, so what was the picture? Let me just remind you. Okay, this was the standard picture we've had. This is the Simon's cone C33. Okay, and then we had here, for example, I think we called this one here S minus. And this one here we called was also S minus, and this one here was part of S plus. S plus, and we can scale these leaves. Now here, what do we get here? So the decay rate here, you can see it here in this height function as we go out to infinity. So what would be the decay here? Would be about r to the minus alpha of C33. This we can check here. This is exactly this alpha 7 here. It was the quadratic cone in 7 dimension, with 7 dimensions of quadratic cone. So this gives us r to the minus 2. We can check. So this decay here, as we go out to infinity, this decay here is decaying like r to the minus 2. If these leaves here decay like r to the minus 2 to the cone itself or towards each other. Okay, now what does this give us? So the trick is now we reinterpret it as a Hölder continuity, continuity of this timestamp function tau. In what sense? I think how did we define this timestamp function tau here? So we look at these leaves here, and so this is C33. I'll just do it now on one side here. Okay, so we have here. Now we scale these leaves down. We get these leaves here, and same as here. Okay, how do we label these leaves? Okay, remember we had to introduce boundary values here. Say we take here distance 1. Now we just intersect this, for example, here with the unit sphere, and now just here move with unit speed here. So this would be, for example, then here be here tau equal to 1. Here would be tau equal to 0. Yeah? And if you do the computation now here, yeah, you see that now here the singular set is here, that close to the singular set here, that tau of x is order of x cubed. You can always check, and you can write this as O of x cubed of 2 plus 1, where the 2 here comes from this decay rate here, and plus 1 comes from the scaling here in this problem. So this means this timestamp function close to a singularity is a Hölder continuous function of Hölder continuous of order 3. Yeah? So this decay rate here at infinity gives you, this means how quickly these leaves, they pull apart very, very fast. You can argue how fast they pull apart. Okay, now we see this already gives us something. Yeah? So, and we can check this works always. Yeah? That's kind of the idea. Yeah? And this is as x goes to 0. We want to understand how does this foliation behave close to the singular set. So this is a simplified model. So what do we get? So we get, let's say, at scales where sigma s and sigma s prime are locally modeled by a minimizing cone C. What we get here, then we know that the combined singular set of all these in between, it's coarsely the dimension of spine C dimensional. That's what we argued already before. And we know that this timestamp function on this combined singular set is coarsely 1 plus alpha of C Hölder continuous. Okay. Now, this is funny. Usually we say function which we know functions on an interval which is Hölder continuous to an exponent bigger than 1, they're constant. Now, this would be kind of optimal here, because if this function would be constant, locally constant, the image would be just points. Okay, but the idea is that the base set here, this combined singular set, can be very fractal. So you can have very fractal sets and functions which are Hölder continuous to a much higher order than 1, but still the function is not constant. To get constancy, you need somehow good connectedness of the set. Okay, but we can still do an estimate. There's a rather easy estimate on the Hausdorff dimension now coming from that. And this is just an easy covering argument. If you want to now estimate the Hausdorff dimension of the image, you can estimate this. You can estimate, you take the dimension of the base set of S locally. And now if you do the computation, you have to divide it by the Hölder continuity. Think of if your Hölder continuous of degree 1, then more or less stretching is preserved. This is no stretching. Then it should have the same Hausdorff dimension. If you have more Hölder continuity, you start pushing the Hausdorff dimension down. You squish things together in the image. So what do we get here? This is less than the dimension of the spine of C divided by 1 plus alpha of C. Okay, and now, this just works at each scale. Now we have to do a very refined and careful covering argument going over all scales, neglecting the scales where we're not close to cones, but it works. So what we do then is in Rn plus 1, now let's do the case n plus 1 is less or equal than 10. This was our first result, where we extended Hart-Simon was 8, and this would be now 9 and 10. Now, what do we know? All non-flat, minimizing cones C have, now you think about if you're at most in R10, then your area minimizing cone can split off at most 2 dimensions, because then what you split off gives an area minimizing cone in R8, which can have only singularity at the origin. If you would split off more like 3 directions, you would get an area minimizing cone in R7, which has to be flat. Then you would split off everything. So they have at most a spine have that the dimension of the spine of C is at most the dimension of the singularity set of C. This is less than n minus 7, which is less or equal than 2. Kind of at most a 2-dimensional spine. Okay, now we iterate this across all scales to get what? Okay, now you get this here. Now you see that the Hausdorff dimension of this image, okay, let's go back to this here. So we use this formula here. Okay, now what do you get for the dimension of the spine of C is 2 at most. And okay, now we go to this here. We go to this, so we know that we're always bigger than 1 here. So we have always this little bit bigger than 1. We can even do it much more carefully, but it's bigger than 1. Remember, so this is 1. The denominator is 1 plus alpha of C. So we have 1 plus a little delta. And we have 1 because this is less than 1. So in dimension, so we see in dimension up to dimension 10, this gives you that the Hausdorff dimension of the image should be strictly less than 1. And we can even say there's a little delta. And this gives us our result. Remember, this was what we wanted to prove. Okay, so the idea is that if you understand how locally around the singularities, the combined singular set, these leaves, that they kind of start pulling apart. And this pulling apart gives us that sort of this timestamp function is Hölder continues to an exponent bigger than 1. We can estimate it, and that then gives you that the image is small. Okay, now, okay, so this is the basic idea up to dimension 10. That's in the last 15 minutes. I'll try to explain you how to get to dimension 11. And dimension 11 is borderline. Now I'll explain you why. Okay, now let's do R11. So this only works on scales. Now you see in dimension 11, then the spine can be 3-dimensional. And you can check here. Then the worst case that if you look at this here, you split off 3 dimensions. Then you have this case that the cone that you split off is the area minimizing cone. This is R3 cross an area minimizing cone in R8. So you have a 2 here. So you would get here 3 divided by 3, which is exactly 1. So it's borderline. So R11 is exactly borderline. So this only works on scales but we can have scales where the dimension of the spine of C is less or equal than 2. Then this argument works. So we cannot handle directly that the dimension of the spine of C is 3. I.e., what do we get? So in this case, what we do have problems is that C is C0 cross R3. So what do we know then? For a minimizing cone C0 in R11 minus 3, which is R8. This is exactly what I just said. Then we have problems, because then we're borderline. Okay, but what can we show? So there's something other interesting to happen now. So we can show, or it's known. Remember we argued here in the beginning that this decay rate is always bounded from below by the decay rate on the quadratic cones. And you can actually show there's a little gap. So the statement is as follows. Can show that alpha of C is, okay, now if you look at this here, you can show it's the same as alpha of C0. So this decay rate only depends here on, if you have such a splitting situation, this decay rate is the same as the decay rate of the product. We have to do a computation. This is equal to 2, in this case, if C0 is quadratic. It's a quadratic cone, but if it's not a quadratic cone, it's bigger than 2 plus some little delta if C0 is non-quadratic. Interesting fact is, it's not known if these guys actually exist. No one has found a non-quadratic area minimizing cone in R8. It's not known if these exist, but we have to handle them. Okay. So what do we get from then? When C is C0 cross R3, and we're modeled on a non-quadratic cone, then everything works again. Okay, because then what do we have? The dimension, the Hausdorff dimension of the image, then locally, we can estimate it by, okay, spine dimension now is at most is 3. And now we have 1 plus this number here, 1 plus 2 plus delta, which again is less than 1, and we have 1 here. Okay, in that case, this is good. So what is the remaining case? What we need to handle is that if C0 is C0 cross R3 and C0 is a quadratic cone CPQ. Okay, now we need to handle this case, we need to do refined Jacobi field analysis. So the idea is now, these cones we can write down, we know how they are, and we can try to understand the Jacobi fields on these cones much better. We have really models now, we can understand it, so we have very good understanding of these Jacobi fields on CPQ. What does this mean? You can more or less write down a Taylor expansion of these. We can write down them in the right. You can not Taylor expansion, some not even Taylor, but like a product formula. With the right polynomials and stuff like that, you can really say, okay, this is a certain expansion in a series, and they always, you can, which coefficients, and you have like harmonic polynomials, positive harmonic polynomials with some factors in front. Leon Simon did this already. So you can more or less really write them down, and if you do this, you get to 2 options. Now this, I'm hiding now a lot of work here, but this is sort of the main idea. 2 options after sort of stratification. I need to carefully stratify the singular set in certain strata. Okay, so if either is one case, so we have that nearby leaves can argue there are 2 options, that either 2 nearby leaves sigma and sigma prime superlinearly. So remember, if we have the same leaves, 2 cones, that they're kind of modeled on the same cone, this means we have a decay rate which is linear. It behave like linear, they're seeing like the same cone. So they superlinearly, so there's a bit more, converge to CPQ cross R3. So this is something like a 3 annulus lemma, or we knew other questions, we use also some kind of discrete frequency function here. So in this case, just to relate back, this gives me that in this case, this tangent cone here is actually strongly unique. Actually, with the decay rate, strongly unique. Tangent cone regime, So you can always argue there are two behaviors. There's a dichotomy. Either these two leaves decay faster towards each other with a certain rate. And then you can actually prove this rate here is reflected again in this Hölder continuity. Then in this case, you can actually argue that the Hausdorff dimension of the image, you gain a bit in the denominator. So this better decay rate, whenever I had 1 plus 2 was borderline, then you can squeeze out a little delta here. So this is using this refined Jacobi field analysis, and this is less than 1. This is again okay. Now, the other option here, the other bad case that can happen is that nearby leaves, sigma and sigma prime, linearly converge, so have slow convergence to CPQ cross R3. So this would be the thing where you usually cannot expect when you have possibly non-unique tangent cones. Slow decay. But then the idea is you have now here, you have now this tangent, this cone CPQ plus this Jacobi field, which you analyze. And remember, we looked at the spine of the cone. And the idea is now you can also look at this, at the translational, the biggest space where these Jacobi fields are translational invariant. So you look at one order higher information, and there you can show on these cones you can gain one dimension by looking at this, at the sort of at the spine of this Jacobi field. Then the dimension, the Hausdorff dimension of this tau of S. Now we do not do the dimension here, so you first would say, okay, dimension of the spine of C here, okay, this would be divided by 1 plus 2 here. Okay, this is not good enough because this up here is 3, but the idea is this here, we can sort of replace this. We look now at this, we can argue that we can replace this by the dimension of the spine of the Jacobi field. We look at the higher order, at the next order information, and look there, what is there, the translational invariant, the maximal space of translational invariance. And this one you can argue, you can gain one dimension, 2 divided by 1 plus 2, which then again is strictly less than 1. So the idea is, in this bad case, repeat, in this bad case here, when we but really know this exactly, you have to do a rather refined analysis. You understand the Jacobi fields much better. Doing this, you can then build a dichotomy. So either you have fast decay, you have very fast decay, then this faster decay gives you better Hölder continuity here. Or you have slow decay, where more or less the behavior of the Jacobi fields kick in. And then you look at the next order information and look what is to next order the highest dimension of like translational invariance, sort of how, and there you can argue, you can analyze these Jacobi fields and can actually argue you gain one dimension. So that this translational invariance of these positive Jacobi fields on this cone CPQ cross R3 is at most 2-dimensional. So you kind of, there's one dimension gets killed there. And that again then gives you this estimate, so you can get to less than 1. Okay. This is where I wanted to stop and see if there are any more questions.
Do you have any questions?
So what do you mean by the strong uniqueness? Is it just the uniqueness of tangent cones?
No, it's here. Strong uniqueness means you actually have a decay rate towards the tangent cone. So it's not only unique, but there's actually a rate of convergence to the cone. You can prove there's like an r to the delta, that it decays like r to the delta.
Okay. some glitch. Felix, could you, so in the last argument, you seem to have this two-dimensional spine, and then you have these R2 translations.
It's a three-dimensional spine. The spine is
three-dimensional spine.
Yes.
So how
But
can you elaborate this a little bit more? And then you claim that you get a better you get a better count on the dimension there, so that the Jacobi.
So you have a three-dimensional spine, yeah, and we know the cone in the cross section very well. This is this quadratic cones, yeah. Okay, and I'm hiding now a lot, yeah. I'm just saying, okay. Then the idea is to do a very refined analysis. We need a kind of discrete frequency functions, many things there. The idea is you can then split it into two cases. One case is that we have kind of fast decay. That means where it's sort of this, the effect of the Jacobi field is not the dominating effect. Yeah, we get there's a kind of a fast decay. So this means the convergence towards this leaf is faster than expected just by the cone. Yeah. This then makes this faster decay towards this tangent cone gives a tiny delta that you can make the Hölder continuity of the timestamp function a bit better. We gain a little bit in the denominator. Now, if that is not the case, then you can argue that this higher order Jacobi field behavior is the dominating behavior, that then dominates the picture. And then the idea is you look actually at the pair. You have the cone plus the positive Jacobi field. Yeah? Now you can think about, okay, you could have Jacobi fields which just split as the cone splits. Huh? But you can prove that these Jacobi fields, these positive Jacobi fields, they don't exist on this cone. They are now on this combined cone, yeah? This cone with these Jacobi fields, where you look the maximal translation invariant of this Jacobi fields can be, you lose one dimension. You have here, this translational invariance of these guys can be at most two-dimensional. So you gain one, so to one higher order information lets you gain one more dimension.
I see. So you do sort of a splitting of the Jacobi fields into these two parts, and then you say there can't be any Jacobi fields on the on that.
Yeah, you can't have a Jacobi field which splits three dimensions and is still positive. That you have to argue that this model does not exist.
Doesn't exist, right? I see. And then you're down to the spine somehow.
Yeah, somehow you have like a new spine. The new spine is the spine of this Jacobi field, yeah. And you can argue the spine of the Jacobi field can be at most two-dimensional, not three-dimensional. So you kind of do a one higher order Taylor expansion.
Okay.
And then see in this one higher order Taylor expansion, the maximal spine gives you that the maximal spine is one dimension lower.
Okay.
Yeah. So if you kind of think of a problem, you do an expansion, and you say, okay, I do this first order expansion. I see sort of my bad set is modeled kind of in something three-dimensional. Yeah. Now I argue, okay, in the only really important case, I can do one order higher expansion. And there's one order higher expansion. I see there is an obstruction towards actually having this whole three dimensions. You only see two dimensions, and that then you leverage on that.
Okay. Thanks.
Any other question?
Could you describe again the final step where you iterate across all scales?
It's a bit difficult to describe. It's a long argument. Yeah. So more or less, it's a covering argument where you start to look at certain scales. You cover your singular set with balls at this scale. Yeah. And then you go one scale down and do a recovering. And in the end, you start you not understand how the image of this timestamp faction behaves from one scale towards the other. So at each scale, you kind of get a rough Hölder continuity, yeah. And you have to kind of go up from you start building a tree, yeah. You start at one scale, you cover your singular set with say balls of radius 1/2 to the 1/2 to the power 1,000, yeah. And then you have all these balls, yeah, which are kind of like rather good covering, yeah, and then you take one of these balls and now you say, okay, you go one step down and you start covering again the singular set on this refined balls. Now you understand how this map behaves from scale to scale. Yeah? This is like Hölder continuity, discrete Hölder continuity. You go like, yeah, and then in the end, you can do this in this way to understand, okay, at each scale, you know that you're kind of modeled on a certain cone, yeah? So you get kind of a rough Hölder continuity, a rough spine dimension. And the idea is you go through these scales and you can argue that you can add up these kind of series in the right way, yeah? And then use this to get an estimate in the end by sort of, look, you first go top down and then you end sum up from sort of the smallest scale to the biggest scale. That's the rough idea.
Thank you.
Are there any questions?
Thank you very much. I think I missed two major points. One is in all this, you proved that Hausdorff dimension of tau s is less than 1. So why is that so important? Sorry, I am little.
No worries. I'll share
I mean,
it again.
the fact that it's less than 1.
Yeah, I'll explain this again. Let me point this out. So recall, this was the setup here, yeah?
Right.
So you had this timestamp function, yeah?
Yeah.
Remember, we had restricted this timestamp function to the singular set, to the combined singular set.
Right.
And we look at this image of this combined singular set, okay? So this means if this image here, we look at this in this interval 0 delta here.
Right.
So this means if this has Hausdorff dimension less than 1, this means if I take any interval, any subinterval in this interval, let's say call it 0 delta or take 0, 1, for example, yeah? If it's Hausdorff dimension, then in every small interval there have to be points which are not in the image.
Right.
Okay, and if I'm not in the image, what does this mean? This means this pre-image is empty. This means this leaf does not have a singular set.
Right.
Okay.
So
this means I find parameters. They're always parameters where I have no singular set. So this means not having a singular set means the minimizer is smooth.
Right. And yeah, I got it. And the other question is, you started with perturbations along the normal directions. Supposing you had was this because of the beautiful foliation structure, or was it, is it the most general thing you can do? Can you also take perturbations along other directions? And
you need in the end a foliation, as Franz pointed out yesterday. The main thing you need to produce a foliation by area minimizers. Yeah.
Right. So that's why the normal.
You need to kind of take the normal. This is why it's restricted to codimension 1. Yeah. Otherwise, you do not have foliations. Yeah.
Right.
Or you could.
Right.
Yeah. Not this one-sidedness. Yeah. It's a way, if you look at this problem with boundary, to produce something which produces a foliation. Yeah. And if you think about it, this is the natural thing, how you expect that you could produce a foliation of minimizers. Yeah. If you have another way of doing it, yeah, if you look at this problem like in this theorem 2 that we discussed end of yesterday, where you kind of change the metric, there also the main work was to produce a foliation. Yeah, to make the minimizer move to one side.
Okay, thank you so much.
Are there any questions? So if there are no questions, let's thank